There are nights when you look up at the stars and feel small. Nights when the weight of infinity presses down on your chest. When you realize that every point of light up there is a sun, perhaps with worlds circling it, perhaps with their own stories written in fire and ice and time. But smallness is not the worst thing you can feel under that sky. The worst thing is knowing. Knowing that out there, 64 light years from where you stand, there exists a world so hostile, so fundamentally wrong, that it makes every human nightmare look like a pleasant dream. A world where the sky bleeds molten glass, where winds scream at speeds that would circumnavigate our entire planet in 2 hours, where the very laws of chemistry have conspired to create hell's blueprint. Its name is HD 189733b, and tonight we're going there. The year was 2005. Humanity had been searching for other worlds for barely a decade, our instruments still crude, our methods still experimental. We were children playing with magnifying glasses, trying to see mountains on distant shores. The telescope was called Elodie, perched in the French Alps, and it was doing something that would have seemed like magic to our ancestors. It was measuring the wobble of a star. Not just any star, a K-type dwarf, smaller and cooler than our Sun, cataloged with the clinical designation HD 189733b, 64 light-years away in the constellation Vulpecula, the little fox. The star was wobbling. Not much, a few meters per second, a velocity you could match on a bicycle. But that wobble told a story. It said, "I am not alone. Something massive is circling me, tugging on me with its gravity, making me dance." The mathematics of orbital mechanics, refined over centuries from Kepler to Newton to Einstein, allowed us to decode that dance. The invisible partner was huge, roughly the mass of Jupiter, our solar system's giant. But it was doing something no gas giant in our neighborhood would ever do. It was orbiting its star once every 2.2 days. Not years, days. It was so close to its sun that its atmosphere was cooking at over 1,000 degrees Celsius. We called it HD 189733b, the lowercase letter, a humble designation for something so profoundly alien. When we found it, we didn't understand what we were looking at. We thought hot Jupiters, these massive planets hugging their stars in suicidal embraces, were mistakes in the cosmic assembly line. We were wrong. The universe makes these all the time. It makes them, and then it torments them with physics that borders on cruelty. But HD 189733b was special even among its tortured siblings, because we could study it, because its orbit, by sheer geometric fortune, carried it directly between us and its star every 2.2 days, creating a transit, a miniature eclipse that let us analyze its atmosphere as starlight filtered through those alien clouds. And what we found in that atmosphere changed everything we thought we knew about weather. Let's establish the basic facts, though basic feels like an obscene word to use for a planet that defies basics. HD 189733b is approximately 10% larger than Jupiter. Its mass is slightly greater, about 1.13 times that of our solar system's giant. These numbers might sound modest, but compress that mass into that size, and you get a density that speaks to a world made primarily of hydrogen and helium, a gas giant, but one that's been bloated by intense heat like a balloon held over a flame. Its orbit is a whisper away from its star. Only 4.5 million kilometers separate planet from sun, a distance that is less than 2% of the gap between Earth and our own star. Mercury, the scorched innermost planet of our solar system, orbits 30 times farther from the Sun than HD 189733b does from its star. Imagine living in a house where the fireplace takes up 98% of the room. Now imagine you can never leave. The orbital period, 2.2 days, means this world is locked in a gravitational prison. One face is always staring at the star. One face is always turned away. There is no day-night cycle, no reprieve, no seasons. The day side is a furnace that never cools. The night side is still hellishly hot, but several hundred degrees cooler than its burning twin hemisphere. This temperature difference, this gradient of thermal agony, is the engine that drives everything else. It creates a pressure differential so extreme that the atmosphere doesn't just move, it screams. When this planet was forming 4.5 billion years ago in the primordial disk of gas and dust around the young star, it didn't form here. The laws of planetary formation won't allow gas giants to coalesce so close to a star. The radiation pressure, the intense heat, the stellar wind, all of it would blow away the hydrogen and helium before enough could clump together. So HD 189733b formed farther out, in the cold outer regions where gas giants belong. And then something happened. Perhaps the gravitational tug of other planets, perhaps interactions with the remaining disk of debris, perhaps the chaotic dance of the early solar system's settling. Whatever the cause, HD 189733b began to spiral inward, falling toward its star over millions of years, surrendering to gravity's long pull until it reached this final terrible orbit. It should have fallen into the star entirely. The fact that it stopped here, that it found this equilibrium of mutual destruction, is either a cosmic coincidence or evidence that we still don't understand the full mathematics of migration. Either way, it survived its journey, and survival, in this case, was a curse. Imagine you could descend into HD 189733b layer by layer, peeling back the curtains of this atmospheric nightmare. What would you find? Let's start at the top, where the atmosphere bleeds off into space, and work our way down into deeper circles of the inferno. The exosphere, the outermost layer, is where the planet's atmosphere is being slowly torn away by stellar wind and radiation. HD 189733b is so close to its star that it's being evaporated, losing approximately 600 million kilograms of mass every second. That sounds catastrophic until you remember the planet weighs roughly 400 trillion kilograms. It would take hundreds of billions of years to evaporate completely. The star will die first. The planet will outlast its tormentor, a cold corpse drifting through the dark. But for now, the evaporation continues, creating a comet-like tail of hydrogen streaming behind the planet as it circles. Below the exosphere lies the thermosphere, where temperatures soar above 1,000 degrees Celsius on the day side. Hydrogen molecules are breaking apart into individual atoms from the sheer kinetic energy of heat. This is not weather as we know it. This is chemistry at the edge of stability. The stratosphere, if we can call it that, is where things become truly alien. On Earth, our stratosphere contains ozone, which absorbs ultraviolet light and creates a temperature inversion, a layer that gets warmer with altitude. HD 189733b has a similar inversion, but it's not caused by ozone. The culprit is likely a hydrocarbon haze, complex chains of carbon and hydrogen forged in the intense radiation, creating a smog that would make our worst industrial pollution look like mountain air. And then, in the troposphere, in the lower reaches where pressure climbs and clouds form, we encounter the silicate layer. Silicon and oxygen, the building blocks of sand, of glass, of the very rock beneath your feet, exist here in vaporized form. On the scorching day side, silicate particles remain gaseous, invisible, mixed into the hydrogen hellstorm. But as the atmosphere races toward the night side, driven by those 1,000-kilometer-per-hour winds, it cools just enough for a phase change to occur. The silicate condenses, not into solid crystals, into liquid droplets. Molten glass suspended in an alien sky, each droplet no larger than a grain of sand, but heated to temperatures that would melt lead. And then, responding to gravity's call, they fall. They fall in sheets, in curtains, in torrents, a rain of glass, each droplet a tiny shard of hell. But they don't fall straight down, because the winds won't let them.
Let's talk about what glass actually is, because most people have never thought about it. Glass is silicon dioxide, the same molecule that makes up quartz, the same molecule that comprises roughly 60% of Earth's crust. On our world, silicon dioxide is stable as a solid, except under extreme conditions. You need temperatures above 1,700 degrees Celsius to melt it. You need specialized furnaces, modern technology, human ingenuity. Nature doesn't make molten glass on Earth, not easily, not often. Volcanic lava can contain silicates, but they're mixed with dozens of other compounds. Lightning striking sand can create fulgurites, those strange tubes of fused glass, but they're rare curiosities. On HD 189733b, glass is a weather phenomenon. The chemistry is straightforward, brutal in its simplicity. On the day side, where temperatures hover around 1,000 degrees Celsius, silicon and oxygen atoms remain bonded but vaporized, a gas mixed into the hydrogen envelope. The entire day-side atmosphere is saturated with silicate vapor. But atmospheric circulation, driven by that massive temperature gradient between day and night, pushes this silicate-laden air toward the night side. And as it crosses the terminator, that razor-thin boundary between eternal day and eternal night, it cools. At around 900 degrees Celsius, a threshold is crossed. The silicate vapor reaches its condensation point. Suddenly, nucleation begins. Tiny seed particles, perhaps dust grains, perhaps other condensates, provide surfaces for the silicon dioxide molecules to cling to. The vapor transitions to liquid, forming droplets, millions of droplets, billions, trillions, condensing out of the sky like a fog, except this fog is molten glass, heated to temperatures that would ignite paper on contact. Gravity takes hold. The droplets begin to fall. On Earth, raindrops fall at terminal velocities of about 20 kilometers per hour, their descent slowed by air resistance. But HD 189733b's atmosphere is denser, hotter, more turbulent, and the wind, that God-forsaken wind, is screaming horizontally at velocities that defy comprehension. The glass droplets don't fall vertically. They can't. They're caught immediately in the jet stream from hell, accelerated horizontally, whipped across the terminator line at 7,000 kilometers per hour. 7,000 kilometers per hour. That's Mach 5.7. That's more than twice the speed of the fastest bullet ever fired. That's faster than the International Space Station orbits Earth. And these winds aren't a localized phenomenon, a tornado or hurricane. They're planetary. They circle the entire equator of HD 189733b in a permanent, unending gale. The glass rain doesn't fall so much as it's fired, each droplet a microscopic projectile moving at hypersonic speeds. If you stood on HD 189733b, if your body could somehow survive the 1,000-degree heat and the crushing atmospheric pressure, the glass rain would shred you at the molecular level. It would be like standing in front of a sandblaster, except the sand is molten and moving at orbital velocities. There would be no pain, no time for pain. You would simply cease to exist as a coherent structure, your atoms scattered into the howling dark. The glass rain falls continuously on the night side. It has been falling for billions of years. It will fall for billions more. A storm without end, without mercy, without meaning.
Where does wind come from? On Earth, it's the product of temperature differences creating pressure gradients. Hot air rises, cold air rushes in to fill the void, and the Coriolis effect from our planet's rotation adds that characteristic spiral. Our fastest winds, the jet streams at altitude, reach perhaps 400 kilometers per hour. Our most violent hurricanes produce gusts up to 300 kilometers per hour. These are forces that can level cities, that can reshape coastlines. HD 189733b laughs at our hurricanes. The mechanism is the same, but the scale is apocalyptic. The day side of the planet absorbs stellar radiation continuously, heat pouring in without pause, without night, without winter. The night side radiates heat into space, cooling down, but never reaching anything we would call cold. The temperature difference between day and night is estimated at several hundred degrees Celsius. That differential, stretched across a hemisphere, creates a pressure gradient that beggars description. Air on the day side is superheated, expanding, creating a zone of high pressure. Air on the night side, slightly cooler, contracts, creating lower pressure. And the atmosphere, obeying the fundamental laws of thermodynamics, rushes from high to low pressure. It rushes at 7,000 kilometers per hour. But here's the part that makes it even more surreal. The wind isn't chaotic, it's organized. Spectroscopic observations, measurements of the Doppler shift in the planet's atmospheric absorption lines, have revealed that HD 189733b has an equatorial jet stream, a river of air that circles the planet at those incomprehensible speeds. It's concentrated at the equator, driven by the temperature gradient and shaped by the planet's rotation, which, despite the tidal locking, still influences atmospheric dynamics. The planet rotates once every 2.2 days relative to the background stars, the same period as its orbit, which in human terms is still rotation. That rotation, combined with the pressure gradient, creates a super-rotating atmosphere, winds that move faster than the planet's own surface. This isn't unique to HD 189733b. Venus has a super-rotating atmosphere, winds that circle the planet in 4 days, while the planet itself takes 243 days to rotate. But Venus's winds are a gentle breeze compared to this. HD 189733b has taken the concept and amplified it into something that borders on the physically impossible. The energy required to maintain these winds is staggering. We're talking about moving quadrillions of tons of gas at hypersonic velocities, constantly, without pause. Where does the energy come from? The star. The relentless input of stellar radiation dumped onto the day side hour after hour, day after day, millennium after millennium, provides an effectively infinite power source. The atmosphere is a heat engine, and it's running at maximum throttle, converting thermal energy into kinetic energy with brutal efficiency. Imagine the sound. On Earth, wind makes sound by creating turbulence, by shaking objects, by compressing air in oscillating patterns. On HD 189733b, the wind itself is a continuous sonic boom, a wall of compressed air moving faster than the speed of sound in that hot, dense atmosphere. The entire night side would be filled with a roar that would rupture eardrums instantly if you had ears to rupture. But you wouldn't hear it. You'd be dead long before your auditory nerves could process the signal. The wind shapes everything. It determines where the glass rain falls, blasting it horizontally across the terminator. It creates turbulence, eddies the size of Earth, vortices that would make Jupiter's great red spot look like a dust devil. It prevents the night side from ever truly cooling down, constantly transporting heat from day to night, maintaining an equilibrium of misery. And it never, ever stops. Tidal locking is a prison sentence written in the language of orbital mechanics. To understand why HD 189733b shows the same face to its star forever, you need to understand tides. And to understand tides, you need to understand gravity's cruelty. Gravity isn't uniform. When you're close to a massive object, the side of you nearest to that object experiences slightly stronger gravitational pull than the side farther away. This difference, this gradient, creates a stretching force called a tidal force. On Earth, we see this in the oceans. The moon pulls on the water facing it more strongly than it pulls on the water on the opposite side of the planet, creating bulges, creating high tides. The Earth rotates beneath these bulges, giving us 2 high tides per day. But tides don't just affect water, they affect solid matter. The moon is stretching Earth itself, deforming the rock, creating tidal bulges in the planet's crust that rise and fall by several centimeters as we rotate. This deformation creates friction, heat, and over time, it's been stealing rotational energy from Earth, slowing our rotation. 4 billion years ago, an Earth day was perhaps 6 hours long. Now it's 24. The moon is also drifting away from us, gaining orbital energy as Earth loses rotational energy. Eventually, billions of years from now, Earth will become tidally locked to the moon, one face always staring at it, our rotation period matching our lunar month. HD 189733b went through this process much, much faster. It's so close to its star that the tidal forces are immense. The star's gravity raised massive bulges on the planet, in its atmosphere, in whatever solid layers might exist beneath. These bulges resisted the planet's rotation, creating friction, generating heat, and draining rotational energy. Over millions of years, the planet's rotation slowed and slowed and slowed, until finally it reached the inevitable equilibrium. 1 rotation per orbit, 2.2 days. 1 face locked forward, 1 face locked backward. This is a stable configuration, the lowest energy state. The planet can't escape it without some external force adding energy back into the system, and there's nothing out there to do that, so the lock is permanent. Forever. Until the star dies, 1 hemisphere will burn. The day side is a landscape of endless noon. If you could stand on the surface, if there is a surface beneath those clouds, you would see the star hanging motionless in the sky, perhaps appearing 10 times larger than our sun does from Earth, a baleful eye that never blinks, never sets, never offers relief. The horizon would glow with permanent twilight, the terminator line a circle of dim red fading into the direction where night reigns.
The night side is a landscape of endless midnight. The star never rises. The only light would come from starlight, from the faint glow of distant suns, and perhaps, if the clouds permit, from the reflected light of the day side, a hellish glow on the horizon, showing you the furnace you're fleeing from. But the night side isn't cold. It's still hundreds of degrees Celsius, kept warm by the constant wind transporting heat from the day side, by the infrared radiation from the clouds themselves. Tidal locking has created a world of extremes, a world divided against itself, a world where half is too hot and half is not hot enough, and the atmosphere spends eternity trying to balance the scales, failing, trying again, failing, a Sisyphean task played out in thermodynamics.
In 2013, astronomers did something remarkable. They measured the color of HD 189733b, not by looking at it directly. Our telescopes aren't powerful enough for that across 64 light-years. Instead, they watched the planet during its orbit, measuring the tiny changes in the total light from the system as the planet reflected starlight toward us. By comparing the light when the planet was at different phases, like watching the moon go through its phases, they could isolate the light reflected by the planet itself. The result was unexpected. HD 189733b is blue, deep cobalt blue, azure, the color of Earth's oceans on a clear summer day, the color of tropical lagoons, of Caribbean postcards, of paradise. The color is a lie. The blue doesn't come from water. There is no liquid water on HD 189733b. At those temperatures, water can't exist as a liquid. It would be steam instantly and probably disassociated into hydrogen and oxygen. The blue comes from silicate particles in the upper atmosphere, tiny grains, small enough to scatter light, just like the molecules in Earth's atmosphere scatter blue light to make our sky blue. But these aren't nitrogen and oxygen molecules. They're dust, molten silicate haze, particles of the same glass that rains down below, suspended in the upper layers where it's hot enough to keep them vaporized, or at least small enough to remain aloft. These particles preferentially scatter blue light. Red light, with its longer wavelength, passes through. Blue light, shorter wavelength, bounces in all directions. When we look at HD 189733b, we're seeing scattered blue light, the color of the dust that's about to condense into glass and fall as deadly rain. The irony is exquisite. The universe has created a planet that looks like a haven and made it a nightmare. If you showed someone a picture of HD 189733b, told them nothing about it, they would assume it was another Earth, a water world, a place of oceans and possibility. They would be wrong in every conceivable way. Color is information. On Earth, we've learned to associate blue with water, with life, with safety. Our evolution on this planet has wired our brains to find blue calming, to see it as a signal of resources, of survival. HD 189733b weaponizes that instinct. It presents itself as welcoming, and it's a trap. Not an intentional trap, the universe isn't malicious, but a trap nonetheless. A reminder that our intuitions, our evolved responses, mean nothing out there in the cosmos. We are adapted to this world, this one tiny rock, and everywhere else, our instincts are worse than useless. They're dangerous. Scientists who study HD 189733b sometimes call it the blue hell. The name captures the duality perfectly. Beautiful and deadly, familiar and alien,
a world that looks like home and couldn't be farther from it.
How do we know any of this? How can we possibly know the color of a planet 600 trillion kilometers away? How can we measure wind speeds on a world we've never visited, where no probe has ever gone, where no human eye has ever looked directly? The answer is light. Light carries information, not just brightness, not just color, but information encoded in wavelengths, in absorption lines, in polarization, in 1,000 subtle variations that our instruments have learned to read like a language. When HD 189733b transits its star, passing directly between us and the star, it blocks a tiny fraction of the starlight. The star dims by about 3% for a few hours. But if you look carefully, if you measure the spectrum of that starlight before, during, and after the transit, you can see something extraordinary. During the transit, some of the starlight passes through the planet's atmosphere before reaching us, and that atmosphere absorbs specific wavelengths, creating absorption lines in the spectrum, fingerprints of the molecules present in those alien clouds. Spectroscopy is our telescope into the impossible. We've detected sodium in HD 189733b's atmosphere, the same sodium that makes Earth's streetlights glow yellow. We've detected water vapor, hydrogen, helium, carbon monoxide, methane, and dozens of other compounds. Each one creates a unique pattern of absorption, and by comparing those patterns to laboratory measurements, we can identify what's up there. But spectroscopy does more. The Doppler effect, the shift in wavelength when something is moving toward or away from you, lets us measure velocities. When we look at HD 189733b's day side and night side, we see different Doppler shifts in the atmospheric absorption lines. The day side is moving away from us on one part of the orbit, toward us on another, and the night side is doing the opposite. But we also see Doppler shifts from atmospheric motion, the wind. By mapping these shifts across the planet's disk during observations, we've reconstructed the wind patterns, 7,000 kilometers per hour, measured from 600 trillion kilometers away with light. The color measurement used phase curves, the same technique that lets us see the phases of Venus or the Moon. As HD 189733b orbits its star, we see different amounts of its day side and night side. When it's behind the star, from our perspective, we see only the day side, fully illuminated. When it's in front of the star, during transit, we see the night side. By measuring how the total brightness and color of the system changes through the orbit, we can isolate the planet's contribution and determine what color it is. Thermal observations use infrared telescopes, like the Spitzer Space Telescope before it was retired, to measure heat. When HD 189733b passes behind its star, it creates a secondary eclipse, disappearing from view. The total infrared brightness drops, and that drop tells us how much heat the planet is emitting. By doing this at multiple wavelengths, we can map the temperature distribution across different altitudes and different latitudes. These techniques are indirect. They're clever. They're the scientific equivalent of archaeology, reconstructing an entire civilization from broken pottery. But they work. They've allowed us to characterize hundreds of exoplanets, to understand worlds we'll never touch. And every measurement we make of HD 189733b reveals something more disturbing, something more alien, something that pushes the boundaries of what we thought planets could be.
Weather on Earth is temporary.
Storms form, rage, dissipate. Even our most persistent atmospheric features, like the jet streams, meander and change. But HD 189733b doesn't do temporary. Its weather is eternal, locked into patterns by the same tidal forces that locked its rotation. The great equatorial jet, that 7,000 km/h wind, is a permanent feature. It's been there since the planet reached its current orbit, probably billions of years ago. It will be there until the star's evolution changes the energy balance, which won't happen for billions of years more. This is wind on geological timescales, wind as a planetary constant. But the jet isn't uniform. Observations suggest variations, turbulence within the flow, storm systems embedded in the larger circulation. Imagine hurricanes the size of Jupiter's Great Red Spot, vortices large enough to swallow Earth whole, all spinning within the equatorial jet stream, all moving at hypersonic speeds. These storms aren't driven by water condensation like Earth's hurricanes. They're driven by temperature gradients, by differential heating, by instabilities in the flow itself. The day side probably has massive updrafts, columns of superheated gas rising toward space, expanding, cooling at altitude, then sinking back down in a convective cycle. These updrafts would create low-pressure centers, and the surrounding atmosphere would rush in to fill them, creating cyclonic rotation. On Earth, the Coriolis effect determines whether storms spin clockwise or counterclockwise, depending on hemisphere. On HD 189733b, with its slow rotation rate and tidally locked configuration, the dynamics are different, more complex, not fully understood. The terminator line, that boundary between day and night, is a zone of extreme shear. On one side, air is rushing toward the night side at 7,000 km/h. On the other side, air is being pulled back toward the day side. The result is turbulence, eddies, waves propagating through the atmosphere like ripples on a pond, except these ripples are traveling faster than sound and carry more energy than nuclear weapons. The night side has its own weather. The glass rain falls continuously, but not uniformly. There are probably regions where condensation is more intense, where the temperature drops just below the critical threshold and the silicate literally rains out of the sky in concentrated downpours. Other regions might be relatively clear, the glass having already precipitated out, leaving a slightly less opaque atmosphere. But clear is relative. Visibility on HD 189733b would be measured in meters, maybe kilometers at best. The atmosphere is thick with haze, with dust, with suspended particles of a dozen different compounds. Lightning is possible, perhaps even common. On Earth, lightning forms when ice crystals in thunderstorms collide and create electrical charge separation. On HD 189733b, any kind of particle collision in those turbulent clouds could generate static electricity. Lightning bolts on HD 189733b would be hot enough to vaporize any solid matter, long enough to span continental distances, and frequent enough to create a near-continuous electrical discharge across the night side. The upper atmosphere probably has gravity waves, oscillations created when rising air overshoots its equilibrium altitude and then falls back down, creating a wave pattern that propagates horizontally. On Earth, gravity waves create those beautiful rippled cloud patterns you sometimes see at sunset. On HD 189733b, they would be shock waves, pressure fronts strong enough to sterilize anything in their path. Every second of every day on HD 189733b is a storm. There is no calm. There is no eye of the hurricane, no safe harbor, no shelter. The entire planet is the storm,
and the storm is the planet, and both have been locked in this configuration for so long that the boundary between weather and geography has ceased to exist.